during the last session. I promise that today, or during the next section, we'll be proving that the closed interval 0, 1 is a compact set of R endowed with the usual topology. So that's what we are going to do. So, okay, so I'm going to open okay, so yesterday we did not write. So today is the 22nd. Let me change that. So here we are talking about compact sets. Compact. So we have this result. Any closed interval of R is compact. So in particular, we are going to show that the closed interval AB, I mean 0, 1. So that interval 0, 1 is compact. So the proof of 0, 1 will be, I mean, if you want to prove for an arbitrary AB, you can proceed in the like manner. So we fix A equal to 0 and B equal to 1 to do the proof. Okay. So now the proof, we are proving it now. So for the proof, what we do, we take an arbitrary cover of the interval. So let OI, I being in the set of indices, B, the covering of I by open sets. What does that mean? It means that I is contained in the union of the OI. So which means that any element x in the interval 0, 1, close interval, is in at least one of these O sub I. That's what I mean. Right. Now, we are going to construct, so we define W to be the following set. So W is the set of S element of the interval 0, 1 such that, okay, let me search that like this, such that the closed interval 0s has a sub covering by the OI, this exact same OI, has a finite covering, finite subcovering, by this exact same OI. Okay, so this is our W. If you succeed to prove that W is equal to the interval AB, that is the closed interval 0, 1, we are done. Because we have here, we have an arbitrary covering. We want to show that from this same covering, we can still cover a 0, 1, the closed interval 0, 1, with the same O's, but a finite number of them. So you see that by taking S, the first thing to show that this is not empty, otherwise it will not make sense, right? We can show that actually is not empty, but it's even an interval, right? So if you succeed to show that, we are good to go. And the next thing will be to show that W is equal to the interval 0, 1. And if we succeed to do that, we are done with the proof. Right. So how do we know that this is non-empty? So the first step here, W is non-empty. W is non-empty. Why? We can see that 0, if you take S equal to 0, the closed interval 0, 0 is reduced to the singleton 0. Does that have a finite subcovering? Yes, because 0 belongs to at least one of them, and we fix that one, it will be just one, right? We take that particular one, and that will be our finite subcovering. Okay. So we say that 0 is an element of W, since, because to be an element, the closed interval from 0 to that element should have a finite subcovering, otherwise it's not an element. Since the interval 0 for this first 0 and 0 for S, which is reduced to the singleton 0 as a finite subcovering. What is obvious is that 0 cannot belong to all of the, even if it belongs to all of them, we take the we select one of them, and that would be finite, right? So that interval we contain in a single of them. You can just take one of them. We know that it belongs to at least one. Why? Because the closed interval is contained in the union. So if the closed interval is contained in the union, it means that 0 belongs to one of them. So we take that arbitrary one element, one open set to which 0 belongs. Then finished, we are done. So 0 is an element of W. So we can even go further. Because 0 belongs to W, not because 0 belongs to W, we move even from the subcovering here, from this one. We can move further by saying that W is indeed an interval, is an interval. It is an interval, right? Why? 0, the fact that 0 belongs to W, right? We can use the fact that interval of 0, 1. By definition, we know that W is contained, right? Because each element of W is there, right? It's a subset, but we are not sure if it's a sub-interval. Why? Because W can be this. W1, W2, maybe Wn. like that. Or, and you can see that this is not an interval, right? This is a discrete set. Or it can even be the union of Wn like this, when n is an in n. So in other words, it can be a countable union. That's possible. For instance, if we take 1 to the n, all these elements, 1 to the n, if I take 1 to the n like this, it's an element of 0, 1. This one, because n, if you assume that n is non-zero, if n is 1, it will be 1. If n is 2, it will be 1/2, and so forth. So we can take all possible real number here. It will always be in between 0 and 1. And if you take the limit, of this, it will be 0. So you can see have this, but this is not an interval. So Wn, where Wn in that case can be this. But this is not an interval, right? It's countable union. It's not an interval. So, but we are saying that this is not our case. We are not in these cases, right? It's in fact an interval, right? So that is what we want to show, that is in fact an interval, right? Interval. So the precision is worth mentioning, right? For your understanding. Right. So let's do this. We know that 0, because 0 is here, is contained in the union of, so we can find this exists I0 in I such that 0 belongs to OI sub 0. It comes from the fact that the interval is contained in the union of OI. So 0, so any element here is one of the OI. So we take 0 in that OI. But this is open. O I sub 0 open means that it is a neighborhood of 0. Neighborhood for the topology of R, it means that this will contain an interval of the form 0 minus epsilon, so that is epsilon, positive epsilon, negative epsilon, like this, will be contained in OI, because 0 is there in the middle. So this is neighborhood of 0. But we don't need the negative, right? We don't need this part. So we can just take, and we know that this 0 epsilon like this is also contained in that. So finally, O sub I0 will contain so it implies that we can find a positive epsilon such that the interval 0 epsilon I can even close at 0 because we know already. Okay, close is fine. Epsilon like that contained in OI sub 0. So we have this. Okay. So that interval is contained there. This interval is contained. So in other words, what do we say? This interval is contained in the interval 0, 1 and is contained in a finite. So what can we conclude? This is a finite subcovering of the original. So we saw that this all I sub 0 contain the closed interval 0, 1, right? Even more is not only 0, 1, but it contains even, because remember we said that it is this one, so 0 is contained also. 0 is there. So I can even close at 0 here, right? I can close at 0. Right? Or what am I trying to show? I want to show that this same epsilon I want to show that the epsilon is in the interval or is in W. So for epsilon to be in W, what do we need? Okay, I can do this. It's just simple, right? It's simple. Because I want to show that this epsilon is in W, so I need to close it here and there. So I can use this interval the idea is there because I just want to show that this, like this, is contained in a finite number, but I can still use that exact this. Therefore, I will be able to see that epsilon is there also, right? Epsilon is there. And not only epsilon, but the entire sub-closed interval 0 epsilon will also be an element, right? Because if it contains an interval, I mean, it will show that it is contained in the closed interval. It contains an interval, but actually it is an interval, and we can prove it. So the idea, in fact, the simplest way to do that is to say the following. But it will be a bit complicated, but I want you to understand what I'm trying to say here. We have this. I can close at 0 here. It is still there because 0 is there, right? Now, instead of taking that this epsilon, I can subtract 1 by a certain n. I can find such an n such that it is greater than 0, but less than epsilon. We know already that epsilon minus that is less. So we can find something of the form 0, that epsilon minus 1 to a certain n sub 0, like this, that is contained there, right? We can take that. We select this n0 such that epsilon minus that is still positive. And that is possible by density of Q in R. Since epsilon is greater than 0 like this, I can always find a rational number inside here. Right? I can find an element, rational or irrational, in between the two. I just take epsilon by 2. If I take epsilon by 2, okay, it's even simpler like that. Okay, let me just even take epsilon by 2. It's even simpler, right? And that epsilon by 2, I can denote it by a different name. Epsilon by 2, I can still call it epsilon 1, epsilon 2, whatsoever. So that's just what I want to show, that I can always take another epsilon prime less than this epsilon in such a way that I will be able to, but anyway, so I can, as I said, I can find an epsilon prime here. And this epsilon prime, I take it less than epsilon. So this closed interval will be there. So yes, so that is it. Epsilon prime less than that. So in such a way that this closed interval, 0 epsilon prime contained in this is contained in that. Okay, so we can do that. So this comes from the fact that O is open. So that's the information I'm using. So now this epsilon prime, I can recall it epsilon. So I could have just said here that we can find epsilon prime so that the closed interval that is contained, but because it's open, I'm showing that it's possible with open, but that open interval can contain a closed interval which is smaller, and that's exactly what I'm writing here, right? There. So this implies that epsilon prime is an element of W, right? Because this closed interval is contained in a finite number of open intervals. So I have it, even though it will be likely be small, but it's an interval. It is an interval. Okay, so now if this is understood, it's a great step. So we can already see that, okay, it is obvious, I can say it is obvious that this closed interval is contained, not only this, but the entire closed interval is contained there. It's obvious. It's obvious. How is it obvious? If you take an arbitrary element here, it is in WY. If I take any element here in between the two, it will be contained in that O0. I mean, a OI sub 0. Any element that I take here, okay, let me say, let's say alpha, an element of 0, that. Of course, we assume, I will take in the club because we know already that 0 and epsilon primes are in that. So I will just take the closed interval, the open interval 0, epsilon prime, right? I know because alpha is less than epsilon prime, if I take the closed interval 0 alpha, this is contained in this closed interval 0 epsilon prime, which is contained in this OI, which implies that alpha is in W. So I took an arbitrary element of the interval 0 epsilon prime. I show that it is in W. So the entire closed interval is there, right? So when I say it's obvious, it means that you can write it, but I will not keep that here. Okay, so it is contained there. So it contained already an interval, but E itself is an interval. So that is the next thing that I'm going to write. Okay, I wrote it here already. It's an interval. Right. Now, still, if you are not convinced, you have this to show that in an interval, it means that it is something of the form 0 C. Open or close, right? Of course, we know it's closed at 0. It can be open at C, or it can be open or closed at C. So if you want to prove that further, we know that something is an interval if it contains anything in between two of its points. So if you take two arbitrary elements, A and B, in W, if we can show that anything in between is there, then it's an interval, right? But I don't want to do that. So for this one, just take two elements A and B. We could have done it, but I wanted you to see that you can show that an entire interval is there. An entire interval is there. This is something that I did directly. But W itself is an interval. So you take two elements A and B because you know already that there are many points in W, not only a single point 0. This was to show that except 0, there are many others. In fact, there's a whole interval that is there. But it's even there is more than this. So if you take two arbitrary points A and B in W, you just show that. So for this, I'll write it here. If A, B are two elements distinct, of course, of W, right? How would I call that point? Okay, let's call this point C, which is T minus 1 times A plus 1 minus T B is also in W. So if you show that, you show this an interval, right? But the purpose of showing this was just to show that you don't just have one point. You got to show that 0 is there. You might think, oh, why is there any other point than 0? So that was the purpose of doing this. Of course, it will seem as if I'm complicating, but I'm making the things clearer for you. So you just do that, and that is it. You are done, right? Of course, if you take A, W, you know already that 0. And that's just to try to prove that. You know already that 0, A, like this, has a finite sub covering here. And similarly, for this. Of course, I didn't say that T is a value between 0 and 1. Eh? It's a value between 0 and 1. So T is in the interval 0, 1. So if T is 0, C will be equal to B. And if T is equal to 1, C will be equal to A. But we know already that A and B are there, so we can use T strictly or in the open interval 0, 1 to show that it's actually an interior point to those two. Okay, now to show that this is there, you just have to show that 0C, this closed interval, has a finite covering or subcovering. And to show this, you use the fact that this A and this one zero B, this has a subcovering, this has a finite subcovering, That. Obviously, you can assume you can assume that one of the two, because there are two, A and B, are both in R, and they are in the interval 0, 1. So if they are both there, and it means they are on a line, one should be less than the other one. So you can assume, for instance, that maybe A is less than B. You can assume that A is less than B. If A is less than B, this having a finite subcovering is enough, right? Because it will be there. So this AB will be contained there. This having a finite subcovering. In fact, you have that having a finite subcovering. So now for your C, which is this, we can see that this C is contained here, right? C is here. This C, this point C will be, so what I mean is that 0C is contained there. Since this has a finite subcovering, obviously this is contained in that finite subcovering. Consequently, C is there. All right, so that's just for you to see that actually these things are not difficult. You can reason and write down the proof. All right, so it's an interval. So the last thing is to, because it's an interval, we can claim that it is of one of these forms. So W being an interval, W is in one of the form. W is equal to the closed interval 0, C, close like this, or zero, open at C. I can write open at C like this, or I can write open like this. I already told you that it's the same thing. So we have this one, where C is nothing else than the supremum of W, right? Does it exist? Yes, it exists. We know that in R, a subset of R has a supremum if it is non-empty and bounded. And this is bounded, W is bounded by 1. No element of W is greater than 1. So for any element of W, that element is less than or equal to 1. So it's bounded by 1, right? So it is non-empty and bounded, therefore it has a supremum. So that is it. This is our supremum. That is the largest possible interval. So the supremum might be in W or it might be out of W. It might not be an element of W. You know that. But let us show that actually it is there. So if C, the C, which is the supremum, is less than 1, what will happen? There exists a certain J sub 0 in I, right, such that C belongs to O J sub 0. Why are we saying it? C is less than 1. So C is here. So C is here. If it's less than 1, less than or equal. So, but we want to say it's strictly less, we want to show that it is equal to 1, that C is actually 1. So if it is strictly less, it is here, so it is in one of the O's, that's all. So C is in one of the O's, right? And because it's open, we can write a similar thing as the one that we wrote here, right? OJ is open. Open. This implies that we can find two. We can find we can find S1 and S2. We can S1, S2, such that S1 is less than S1 is less than C, less than S2, like this. That is our interval that contains, because this C is there, so OJ sub-0 will contain an interval containing, open interval containing C. That's what it means, right? So we take the open interval S1, S2, which is contained in that. Okay? But we can even take more. So we can find this with S1, S2, both with S1, S2, both in O, right? So in particular, this closed interval is containing W. How do we see that it is containing W? By the exact same procedure we perform here. You can see this one. We can do exactly what we did here. Similarly, similar. You see that here we say that we can find something like this, and we took this closed interval. So we can do something similar such that this also will be satisfied, right? Because it's an open interval, we can write it in such a way that it contains a certain S something. And then we take this S2 to be smaller than whatever S is there in such a way that this is contained in the open interval. Exactly with the way we manipulated here, if you want this to be closed and you have the open here, you take this with the closed but less than this open. So this is always possible. Okay, so we have this, we have that, and beside what we can do, another justification is that we know already that here, this C, we have already the fact that C is in OJ, OJ sub 0. C is there, right? This is there. Now, if you take S1, this is S1. S1 is less than C, which is the supremum, right? But because it's less than the supremum, S1 is an element of W. Because remember that the supremum is this is the supremum of W. Now, if I take an element that is less than the supremum, right? As you can see here, we say that W can be this or it can be that. So if it is the open interval and anything that I would take less than C, I can less than C will be an element of W, right? If I take an element less than C, it's already in W, right? So here, the fact that S1 is less than C, if W is open interval, if it's open here at C, if I take an element that's less, it's already inside W. But C here is at the border, and it's not even. But if it's closed, it's fine. If W is the closed interval 0C, and I take an element is inside W, so it's there. But even if it's open at C, if I take an element that is less than C, it's already inside. It's in the interior of W. Okay, so now, so we know that from what I explained, if it is there, this has a finite subcovering. Right. Now, if we add S2, we know that this S2 is in OJ. So I can add this OJ to the subcovering of this one to cover from 0 to S2. So if I have a finite subcovering for 0S1, and I add I add OJ to that, that will be an extra covering to make sure that the closed interval 0S2 will contain a finite subcovering. So this just shows that S2 is in W, and in particular, the subinterval, the closed interval 0S2 is also in W. Right. Or maybe it might be easier for you to proceed as we did previously. You just take the fact that these two elements, S1 and S2, S1 and S2 are in W. You can show that everything in between is there. And it's true because we already proved here that W is an interval. So anything in between will be there, right? It's an interval. So if I know already that S0 is there, S2 is also there. So the interval 0, S2 is in W because it's an interval. It will contain anything between two of its elements, right? We don't even need to go far, right? Once we show that S2 is in W, we know that 0 is also in W, so the interval, the closed interval 0, S2 is also contained in W. So they are even easier proof. Okay, now what have you just realized? So the fact that so we can add here, since one can add OJ to the family O, J sub 0 to the family or the collection to the finite subcovering of this. Right? So now what do we realize? Look, S2, we saw that X2 is greater than C, right? But this contained in W means that S2 is less than its supremum. But we say that it's greater than the supremum here. So it's less greater than, so that's a contradiction, right? Because I cannot find a greater element an element that's greater than the supremum, but which is still in W, because you can see that here S2 is in W. So if S2 is in W, it automatically leads us to a contradiction, right? So S2 in W contradicts the fact that C is the supremum of W. So if there's a contradiction, this contradiction just indicates that our assumption is wrong. So what is our assumption? Remember, if. So therefore, this is not true. C is equal to A. Thus, okay, maybe to reduce space. So thus, C is equal to 1. C is equal to 1, meaning that W is either the closed interval 0, 1 or close at 0, open at 1. But now the next is just to show that 1 is an element, right? So, and we show in a like manner that this is in W, and then if it's in W, it means that the only remaining is there, it means that C is 1 and it's closed because it's an element of W, right? That is it. Finished. When we say we show it in the like manner, you just take, we saw here that 1 is in one of the OIs. So you take that O and you add it to the covering here, to this covering. So exactly what we did here with S2, you do that to C, right? Do that to C. You have this finite subcovering of 0S1. And we have C here, which is 1. So you take that open set, you add it to this final subcovering, you have a final subcovering, and therefore 1 is in W. Why? Because the closed 0 up to 1 has a final subcovering. So you take the subcovering for 0S1 and you append the subcovering that contains 1. Then you extend that to 0, 1. And that's the end. I think we'll stop here. It's already late. So you see that's not difficult. I took more time to explain, right, in detail the proof. This is not a unique way to do the proof. You can use a different method. There are so many methods that you can use, provided you remain consistent. Right? You could also proceed by contradiction. That is, you assume that is contained here, but it's not contained in any finite subcovering. You construct a sequence that will lead you to a contradiction. So there are many ways, but this is one of the easiest ways, right, to play around the concept. And then, okay, so we stop here for today. I hope you will enjoy this presentation. See you next time. God bless you. Bye-bye.